So I would like for you to turn to 10-20 in your notes. So 10-20, and you're just going to take notes with me as I talk through this. But we're going to talk about the second law of thermodynamics. So we know that the first law of thermodynamics is that the change in internal energy in a system is equal to the amount of heat that flows in or out plus the amount of work that is either done on or by the gas. And so that is the first law of thermodynamics. That is not going to be given on the test, so make sure you guys understand that. The second law of thermodynamics has several ways of saying it. The first way, it says heat energy flows spontaneously from a hot object to a cold object only. In other words, basically they're saying here that heat only flows from hot to cold. Okay, so if I have something with higher temperature, heat's always going to flow to something with lower temperature, TH meaning temperature hot to temperature cold. So we know that temperature hot, of course, is higher temperature than temperature cold. And remember, temperature is the average, the measure of the average kinetic energy. Okay. The one that I want us to know is this second one. It says it is impossible to construct a heat engine that is 100% efficient. A heat engine can convert some of the input heat into useful work, but the rest must be exhausted as waste heat. What that is saying is there's no way for us as humans to create something that is 100% efficient. We're going to lose some energy in the process. So all the energy you put in, the energy, you're not going to get all that same amount of work out. To put that in an example, car engines can be anywhere from 25 to 35% efficient. With the invention of hybrids and all that stuff, it's getting better. But let's say it's about 25% efficient. What that means is only 25% of the gasoline that you put in your car is actually driving the car. All right. Through friction, through just losing some because the combustion reaction doesn't take place all the way, we're losing some energy along the way. Okay. And then the last one says that the entropy of an isolated system never decreases. It can either stay the same or it can increase. And more than likely, I'll do a little demonstration or talk about that a little bit more. But you guys talked a little bit about entropy and enthalpy last year in chemistry. So the second one is the one that I want you to know. But all of these three things are related. And so that's why it says you can state these in several equivalent ways. But I want you to know the second one. We'll talk a little bit more about entropy later on. All right. So then basically we're going to look at the heat engine part. A heat engine is something that takes energy in, right? It takes energy in, it does some work, and then it's going to expel some energy. So it says a heat engine is a device that is capable of changing the thermal energy, QH, also known as the input heat. Make sure you guys know that. QH is the input heat. All right. That's the energy in. Okay. So that's energy in. Okay, that's energy in. That's the energy we're putting into the system. How do we get heat energy to flow? Well, if you look at the picture, you need to put the engine, the thing that's trying to do the work, in contact with something higher or hotter than itself so heat can flow in. So this is QH right here. That's the heat that's into the engine. Okay, then it says into useful work. So the engine does work. So this arrow represents the work. It's doing work on the environment. It says heat engines cannot be made to be 100% efficient. And while part of the heat engine is converted to useful work, useful meaning we actually can do something with it, the remaining heat energy will be rejected to the environment or surroundings as waste heat. So QC, we call that waste or exhaust. So if you want to make a little note that is exhaust, you can do that. That's the amount we're losing. Okay, so then it says from an example, this is the most basic. This is not actually how an engine like works in terms of all its components, but this is the general idea that you have heat in, it does work, and then it exhausts some heat to the environment. We call it QH represents high, and QC means cold or out. So it's in connection with something that is colder than itself. So we take energy in, we do work, and we then lose some energy. So if you think about it, the total energy that comes into the system, some of it goes into work, and some of it goes into exhaust. And so that is this equation. So make sure you understand how to use that. This is the total energy available to us. This is the amount of work done by the engine, the useful work, trying to drive our car forward or whatever we're dealing with. And then that is the amount that we're losing. In an ideal case, what we will want is we want to try to make this as big as possible, which would make that as low as possible. So ideally, in an ideal world, we would want QH to be W. All the energy we put in is being done into work. But we know from the second law of thermodynamics that is not possible. QH will always be bigger than W. We want that. We want this. We want that. But QH will um, QH will always be bigger than W. Okay. So it says in an idealized engine known as the Carnot engine. I know that's kind of cut off right there, but let's go ahead and do that. The Carnot engine. The energy loss due to internal friction or turbulence present in the fuel after ignition are not considered. Okay, so we're saying it's the best of the best real situation we can create. Carnot determined that. Okay, let's move on to the next one. That the maximum efficiency E that could be realized from a heat engine depends on the temperature of the input heat and the exhaust heat. So if I go back, that is the temperature of the high. That's the temperature low. I think I'll call it temperature C to represent the cold temperature. And so going back to this, it says we want TH and TC to be expressed in Kelvin. Now, it makes sense that you would think that efficiency is determined by the ratio of the amount of work that your engine is doing divided by the total amount of energy available. All right. And then we know that from that equation that I showed you guys already, that right there is the connection between heat in, heat out. The difference would be the amount of work done. If we substitute that in there, we can get that. So another way to write this is efficiency. So if you want to make a little note, it says it right there, but that's efficiency. Okay, that's efficiency. So what I could do is I could actually rewrite that as QH all over QH minus QC all over QH. So another way to write this is actually 1 minus the ratio of the exhaust heat all over QH. That is another way to write the efficiency. So that probably would be helpful sometimes as well, writing that down like that. Okay. What Carnot said is that we can relate it through temperatures. So if you think about efficiency, like if we want to be 100% efficient, we would want the work to be the same as QH, just like I have over here, right? We would want the work to be the same as the amount of energy that's given to us, but that's always going to be less than 1. So another way to state the second law of thermodynamics is that the efficiency will always be less than 1. And then if we want it in percentage formula, we multiply both sides by 100, so, or at least the percentage, the efficiency will always be less than 100%. All right, and so what Carnot did, the scientist, was he actually figured this out, that's the ideal. So sometimes this is referred to as ideal as well, like in ideal for real world. Like that's the best that we can happen to have in a real world situation. So it says in order for a Carnot efficient engine to be 100% efficient, it would be necessary for the temperature of the exhaust heat to be at absolute zero. We would want that to be at absolute zero because TH minus TC for zero would be TH over TH would make the efficiency 1, correct? Right, if that went to 0. But we know that is impossible because in order to make something 0, we got to put it in contact with something colder than itself, and there's nothing that can exist below 0 Kelvin. So that is theoretically impossible. So that's why this is this is an ideal situation, like what we can actually do. Now, you need to make sure that for the test that you understand what a Carnot engine is. And so a Carnot engine, if we start here, okay, high pressure, small volume. Okay, high pressure, small volume. It goes to an isothermal expansion. That isothermal expansion means that the temperature doesn't change. So I don't want to write like that. I want to write like this. Write it as delta T equals 0. And then, and we know it's expanding because take a look, there's the second volume. Then it goes to an adiabatic expansion. Remember, adiabatic means that the heat flow is 0. It happens very quickly. All right. And then we get to some really big volume, but low pressure, right? We're at a low pressure right here. Then it's slowly compressed a little bit, isothermal compression, right? And remember, isothermal means that temperature doesn't change during that part. And then it goes to an adiabatic compression very quickly to get back to this. Now remember, for the entire cycle, delta U equals 0. That's for a cycle, right? And so you need to know that a Carnot engine consists of 2 isothermal processes and 2 adiabatic processes. So make sure you know that. If you want to know that it's isothermal, adiabatic for the cycle, that's fine. And remember, to get from there to there, you start and stop at the same pressure and volume. So that means the temperature for the overall thing is not changing. But remember, temperature changes drastically through an adiabatic process. Okay, so that is on the next page. Now, what I want you to do now is now flip over to 10-23. Okay, 10-23, and we're going to work problem number 2 on page 10-23. Okay, it says the hot reservoir of an engine operates at 472 Kelvin. So if you need to take time to pause or whatever to go to this, you can. But the hot reservoir, so that's TH, is equal to 472 Kelvin. And that the cold reservoir, the low end is, the low end is 214 Kelvin. The engine receives 433 joules of heat from the hot reservoir. That's the energy in. So that's QH, which is equal to 433 joules. That is energy in. Okay, that's energy in. It says that the engine's efficiency is 67.2% of the maximum possible. So the actual efficiency, is equal to 67.2% of the Carnot efficiency. Okay, so what that means is that what we're trying to get in real world, the best possible we can do in the situation that we're in, which is E sub C, that Carnot efficiency, the actual, because of friction, all that kind of stuff, is only 67.2% of that. And remember, the Carnot efficiency is the difference in the temperature, so TH minus TC all over TH. We're relating that to the high temperature. So what I could do is I could plug that into there after plugging in the high temperature and the cold temperature respectively. Okay, sorry about that. And also the high also needs to go there. And so you'll get a value for the actual. Okay, so that's what we would just typically just call E, but you would just get a value for that. Okay, so go ahead and do that in your packet. Then take that value, and we know that E, the actual efficiency, is the amount of work done divided by the amount of heat flow into the system. So we already know that. So it says, what is the engine's efficiency? This is part A. What's the engine's efficiency as a percent? So that we've already done part A. This is part A's answer right there. Then part B says, determine the amount of work during each cycle. So what we're going to do is I'm going to rearrange this formula to be W equals efficiency times QH. So what I would do is I would take that efficiency, plug it into there. QH is the amount of heat that we're given. We already know that. That's right there. And I will get a value. Then it says for part C, so that's part B. Part C says how much heat is absorbed by the cold reservoir. That is QC. How much heat basically gets exhausted per cycle. Well, we know that in order to find work is the difference between the energy in and the energy out. You could often think of it as the total energy in is some goes to work and some goes to energy out. Right? Q, remember heat is energy flow. So if I want to rearrange this equation, I get that QC is equal to QH, the total energy, minus the amount of work done. So the heat that is available to do work minus what actually gets done for work is what gets expelled every single cycle. So if you think about this in terms of a car engine, this could look at as a piston, right? There's so much gasoline that goes in the piston, so much stored energy in this combustion reaction that's getting ready to take place. It then spark plug fires, there's work done by the piston, but then some of that gasoline mixture might not fire. Some of that gasoline might not be the correct ratio of air to gasoline. Some of it just might not combust. Whatever happens, we're going to lose some of that energy along the way. We're also fighting friction in the pistons. We try to help that out by using oil to lower the coefficient of friction so that we're not losing as much energy. So there's lots of things that kind of go into this. So what I want you to do is try this problem, and then you're going to show this to me in class tomorrow for a grade. So make sure you have all the answers. If you want to write all the answers kind of like over to the side in the packet, just A, B, C, and just label them with appropriate units, then you're going to be good to go.